Le Chatelier's principle is a fundamental concept in chemistry that describes how a system at equilibrium responds to external changes. Imagine a delicate balance, a scale perfectly poised with weights on either side. When you add or remove weight from one side, the scale tips and the system must adjust to restore equilibrium. This principle applies not just to scales but to chemical reactions as well, particularly reversible reactions, which can proceed in both the forward and reverse directions. At the heart of Le Chatelier's principle is the idea that if a dynamic equilibrium is disturbed by changing the conditions, the system will respond in a way that counteracts that disturbance. This can involve changes in concentration, temperature, or pressure. Let's break these down one by one. First, consider concentration. When the concentration of one of the reactants or products in a reversible reaction is altered, the system will shift to counteract that change. For instance, take the reaction of nitrogen gas and hydrogen gas forming ammonia. If we increase the concentration of nitrogen, the system will respond by producing more ammonia, shifting the equilibrium to the right. Conversely, if we remove ammonia from the system, the equilibrium will shift to the left, favoring the production of reactants. This adjustment occurs because the system seeks to minimize the change imposed upon it, striving to restore a new equilibrium state. Next, let's discuss temperature. Temperature changes can have a profound impact on the position of equilibrium, especially in exothermic and endothermic reactions. An exothermic reaction releases heat, while an endothermic reaction absorbs heat. According to Le Chatelier's principle, if the temperature of an exothermic reaction is increased, the system will shift to favor the endothermic direction, absorbing the added heat and thereby reducing the temperature. For example, consider the synthesis of ammonia from nitrogen and hydrogen, which is an exothermic process. If we increase the temperature, the equilibrium shifts to the left, favoring the reactants. Conversely, if we decrease the temperature, the system shifts to the right, promoting the formation of ammonia. This temperature dependency is crucial for industrial processes, where controlling reaction conditions can optimize yields. Finally, let's explore the effect of pressure. Pressure changes primarily affect gaseous reactions, where the number of moles of gas on either side of the equilibrium can differ. When pressure is increased, the system will shift towards the side with fewer moles of gas to alleviate the pressure. For instance, in the reaction between nitrogen gas and hydrogen gas to form ammonia, there are 4 moles of gas on the reactant side, 1 mole of nitrogen and 3 moles of hydrogen, and only 2 moles on the product side, 2 moles of ammonia. If we increase the pressure, the equilibrium will shift to the right, favoring ammonia production. Conversely, if the pressure is decreased, the system will shift to the left, favoring the formation of reactants. This principle is particularly important in chemical manufacturing, where optimizing pressure can lead to higher product yields. In summary, Le Chatelier's principle elegantly illustrates the dynamic nature of chemical equilibria. It reveals that reversible reactions are not static but are constantly adjusting to external changes. Whether it's an increase in concentration, a shift in temperature, or a variation in pressure, these systems strive to counteract disturbances and restore equilibrium. Understanding this principle not only deepens our comprehension of chemical reactions, but also enhances our ability to manipulate conditions in various applications, from laboratory experiments to large-scale industrial processes. By grasping the nuances of Le Chatelier's principle, we gain insight into the intricate dance of chemistry, where balance and change coexist in a delicate interplay.